This is stellar evolution. Stars form in similar ways, yet minor discrepancies can alter the outcome vastly. For reference, throughout this lesson, know that our star, the Sun, is a yellow dwarf with a radius of 432,690 miles and a surface temperature of 5,788 Kelvin. This lies in the average, middle section of the HR diagram. Stars larger than our Sun, labeled supergiants, can have 10 to 70 solar masses and a brightness from 300,000 solar luminosities and up. This is just the average for supergiants. There are often outliers that exist, like the VY Canis Majoris. Smaller stars also exist in our galaxy. For example, red dwarfs. They're not only dimmer, but 0.8 to 0.5 solar masses. Let's go further into the lives of these smaller stars. All stars form in a region of space called a nebula. This is a cloud of dust and gas, mostly hydrogen and helium, that remains in equilibrium. After a certain period of time, gravity overcomes the internal pressure and equilibrium is broken, leading to fragmentation of clusters of conglomerated material. Fragmentation occurs for thousands of years as this clump grows smaller and smaller, increasing the density exponentially. The fragment eventually reaches a point where radiation from the core can't escape and internal pressure skyrockets, leading to more stabilization of this new protostar. The protostar has entered a phase called the T-Tauri phase. The heat will continuously rise for millions of years until it reaches 10 million Kelvin. This is enough to overpower proton repulsion and undergo nuclear fusion. This marks the true birth of a star, where the internal pressure from burning hydrogen equalizes gravity, known as hydrostatic equilibrium. The new star now lies on the main sequence of the HR diagram, where it will live 90% of its life here. All stars form through nebula accretion, but their life is dictated by the amount of material that fragments during collapse. Smaller stars can live for billions of years, even reaching up to 1 trillion years because of their size. They actively burn less fuel to remain in equilibrium, so the fuel conservation rate is more efficient. At this point in their life, they thrive on the main sequence in the lower right region. When the hydrogen supply is depleted, gravity takes over and initiates another collapse. This leads to the core heating up, allowing the smaller star to fuse helium as its new source of internal pressure, creating heavier molecules as a byproduct. When this helium runs out and the stars have nothing left to burn, they drift slowly upward in the left direction of the HR diagram, as the imbalance inflates this star to a red giant. Combined with stellar winds and shell flashes, the layers of the star are blasted apart, leaving a planetary nebula. The planetary nebula retains its heat in a small core. As the rest of the heat drifts away and the core cools, a white dwarf is all that remains. The smallest stars are theorized to fizzle out into white dwarfs without the explosion into a planetary nebula. No small star has died yet. Both white dwarfs, from a medium star to a small star, they have no energy source, but they have extremely high surface temperatures. They'll continuously cool as the heat radiates away. Finally, the white dwarf loses all heat, cooling into a black dwarf, an object that lacks light. Currently, no black dwarfs exist. Larger stars form the same way that smaller stars do, but with a larger amount of mass. This drastic increase in the mass is the downfall of this star, as more hydrogen must be burned in order to keep it in equilibrium, shortening its lifespan to billions, if not millions, of years. These stars lie in the upper region of the graph, dependent on their luminosity. Like the smaller stars, massive stellar objects deplete their hydrogen fuel and begin to fall victim to gravity. The core will become a high enough temperature to burn carbon to oxygen, neon, silicon, sulfur, and finally to iron. This will keep the star alive until all options are gone. When this happens, the star's core collapses, leading to nuclear temperatures. To avoid the collapse, the high-density core causes infalling matter to reflect off the core. The bouncing material and collapsing core leads to a massive explosion called a supernova. Supernova explosions inject carbon, oxygen, silicon, and other heavy elements up to iron into interstellar space. If the supernova is small enough, neutrons are consolidated into the core to form a dim neutron star, only detected by pulsars, or the beams of light that are ejected from the poles. Supernova remnants of large stars can form black holes, a gravitational well that even light cannot escape. Here we observe an artist's rendition of what a supernova looks like. Supernovas scatter material across the galaxy, providing materials for new planets, new stars, and life.
To review, stellar evolution is heavily dependent on the accumulation of mass in a nebula. This number can dictate whether a star will experience a prolonged death or a cataclysmic explosion of life. All stars form in a nebula or a cloud of dust and gas, and they can either become an average star or a massive star depending on how much mass accumulates. Average stars will inflate to a red giant as their fuel is depleted, eventually getting stripped by stellar winds and shell bursts to a planetary nebula, where it can become a white dwarf and eventually a black dwarf. Massive stars can burn a lot more, but they burn faster, so they have a shorter lifetime. They'll explode into a supernova. Either the core will cool off and become a neutron star, only detectable by the pulsars or the beams of light emitted from the ends, or it will become a black hole from a stellar remnant, which is a gravitational well that even light cannot escape. Observed stellar events and theorized futures combine to create a model that categorizes and dictates how stars will form, live, and die. Thank you for watching my video on stellar evolution, and thank you more for not paying attention.